Hello everyone, welcome to VLSI Career Craft. This is Monica. So in the previous video, we have seen why setup or hold time exist in a flip-flop, and we have defined the setup and hold times, and we have seen the clock to queue delay in the flip-flop. So in this video, we'll concentrate on how do we increase or decrease setup or hold time frames in a flip-flop, and we will see the importance of pipeline architecture, why it is used in the industry, and the significance of performing timing analysis for this pipeline architecture. So let's get started. Firstly, let's recall the definitions of setup time, hold time, and T clock to queue. What is setup time? The minimum amount of time data needs to be stable before the clock edge arrives for the data to be captured correctly. And coming to the hold time, the minimum amount of time data should be held stable after the clock edge arrives for the data to be captured correctly. And what is clock to queue delay? Every flip-flop has a clock to queue delay, that is a propagation delay from clock edge to queue. We have seen the internal structure of the flip-flop and saw why this delay exists in the previous video. Now, let's just add a buffer in a data path and see how the setup and hold time are getting affected. Let's say D dash is the input that we are giving, and it is connected to a buffer, and with the buffer delay it reaches the original input of the flip-flop. And let's say the delay of the buffer is T buff. So how is setup time affected? Let's say the clock is arriving at certain time and the D input has to arrive certain time before the clock for to allow the setup time frame. So now when does the D dash should arrive? It needs to arrive T buff amount of time before the D edge. So what is the effective setup time? It is getting increased. The effective setup time is nothing but setup plus the buffer delay. Now coming to the hold time. Hold time is checked after the clock edge arrives. So let's say the clock is arriving at this edge and D is arriving certain time after the clock edge arrives uh, to allow hold time frame. So now when does D dash arrive? It should arrive T buff amount of time before the D edge. So what happens to the effective hold time? It certainly decreases. So the effective hold time is nothing but T hold minus T buff. So what is the conclusion here? Adding a buffer in the data path increases the effective setup time, that is increases its setup time frame, but it makes the hold time worse, like it decreases the hold time. Now, let's just add a buffer in a clock path and see how the setup and hold time are getting affected. Let's say clock dash is the clock input that we are giving from outside, but it reaches the clock pin of the original flip-flop with certain delay due to this buffer. Let's say delay of the buffer is T buff again. Now, how is setup time getting affected? Uh, if the clock edge is arriving at certain time T, the D is arriving T setup time before the clock edge. Now when does clock dash arrive? It arrives T buff amount of time before the clock edge to because there is a buffer here. So after clock dash arrives, it reaches the clock with certain delay of T buff. Now what happens to the effective setup time? It certainly decreases. It becomes T setup minus T buff. Now coming to the hold time. So hold time is checked after the clock edge arrives. Let's say the clock is arriving and after the T hold time D is arriving. Now when does clock dash arrive? It arrives T buff time, T buff amount of time before the clock edge. So what happens to the effective hold time? The effective hold time increases. So what is the conclusion here? When we add a buffer in a clock path, it helps the whole time, like it increases the whole time frame, but it makes the setup time frame worse. So in these two scenarios, we have seen what happens when we add a buffer or a delay in data path versus what happens when we add a delay or buffer in a clock path. It's really important to understand this concept because in the industry, the designs have lot of buffers in it, and each buffer has its own significance. So yeah, it might be added in a different scenarios. Now let's understand what is pipeline or register based architecture. Let's say we need to perform a certain task which takes the time T1. And if we are dividing the tasks into five subtasks, each subtask take T1 by 5 amount of time and it executes in parallel. So what happens? The time period is decreasing, which in turn increases the frequency. That is, the task is performed faster. Let's understand this better by seeing an example of how instruction is executed. Let's say the processor is executing 5 instructions in parallel. And the task one is instruction fetch. So 5 clock cycles, it'll fetch the 5 instructions. So next task will be instruction decode. So after the task A is done for instruction one, it goes to task B, which is instruction decode, and it takes 5 clock cycles to decode 5 instructions. So similarly, it will execute, which is task C and memory access, and then it will write back. So what happens after 5 clock cycles? For each clock cycle with a time period of T1 by 5, we have an output coming out. That is, it increases the throughput. So, in brief, this is the working principle of pipeline-based architecture. So, it has certain advantages and disadvantages. Coming to the advantages, it increases the throughput. As we have seen, after certain clock cycles, for every clock cycles, it will give an output. Uh, so, it increases the throughput of the design. And the second one is efficient utilization of resources. So all the tasks are performed in parallel. So we can see that the resources are efficiently utilized because when the task C is performed, task B is not idle and it is performing the next the same task on the next instruction. So the resources are utilized properly. And coming to the third advantage, the scalability. If we want to increase the performance of the design, we can add additional stages here and increase the design. We need not disturb all these tasks and we can scale the task to for the improved performance. And certainly it has some disadvantages because of adding these registers and all. We need to check the timing, and if the timing violations are there, then we need to add the extra hardware like buffers and inverters to meet the setup and hold checks. So the complexity of the design is increased. So it needs to handle pipeline hazards as well. What are pipeline hazards? Let's say task B and task C are accessing the same data X. So which task needs to access first? Which task, if it is trying to write, task B is trying to write on this variable and task C is trying to read on this variable. So there is obviously a conflict and the execution might be false. So we need to take care of all these hazards. And the second disadvantage is increased hardware. And due to adding all these registers and extra hardware for meeting timing violations, it certainly adds some extra hardware. But in industry, due to these advantages which are seen, this pipeline architecture is preferred by almost all the industries. Now let's discuss the importance of timing analysis in the register-based architecture. Let's take a part of the register-based architecture where there is a launch flop and a capture flop and there is a combinational logic in between. So we try to launch the data, and the second flop tries to capture the data. So for the data to be captured properly, first we need to meet the setup and hold requirements. Then only we see the correct functionality of the design. So to check if these requirements are met, we need to perform timing analysis. And second, to prevent the race condition. What is a race condition? So it is an undesirable condition in a circuit where the output becomes undeterminable. Uh, so let's say in a JK flip-flop, if J, K and clock is 1, we see the output is continuously toggling. So that is a race around condition in the flip-flop. So such race conditions need to be prevented. So obviously we need to perform timing analysis and to determine the maximum clock frequency of the design. When the design is divided into certain subtasks, we need to determine the frequency at which design is working. For this, we need to do timing analysis and come to a conclusion that, yeah, my design is working at this frequency. And to identify the critical paths and optimize them. So what is a critical path? It is the longest path in the design. That is, the longest path adds the maximum delay to the design. So due to this maximum delay, there might be certain timing violations. So we need to optimize this. That is, we need to decrease this the delay of this critical path to so that we can perform the task in uh, lesser time period. That is, we can increase the frequency of the design and we can achieve the higher clock speeds. And fixing timing issues during design phase. So when we are in the initial stages of the chip design, the fixing of timing violations is very important, because going further in the later stages, when we enter into physical design phase, there the fixing timing violations become very costly. So uh, it is important to detect the timing issues in the initial design phases and fix it. So, due to all this, we need to understand the timing analysis, how timing analysis is done for the register-based design properly. So, in this video, we have discussed how setup time and hold time are increased or decreased, and we have also seen the importance of pipeline architecture, and we have seen the significance of timing analysis in this pipeline architecture. So in coming videos, we will discuss some other interview concepts as well. Uh, Please comment and let me know if you want to uh, hear more on some other interview concepts, so that we'll get to know the information from you. Thanks for watching. Happy learning.